All right, if we're going to talk about electrostatic forces, at some point we want to get beyond just being able to say there is, two charges that are acting on each other. A lot of times we want to know, well, what's going to happen if I move a charge into a particular place? And that's when we start talking about electric fields. All right. So we use the concept of an electric field to explain how magnetic forces will function in a given space. You might think about this, you might have heard the phrase gravitational field, right? It's the same idea. So we think of, if a spaceship is in the sun's gravitational field, that means it's being affected by the gravity created by the sun. We're going to do the same thing. If we have a charge or a set of charges, how do they create a field that if a charge moves through that field, it's going to be affected by that field and forced to accelerate in one direction or another? So this is a force field that allows us to visualize the forces that would act on any charged particle that entered that space in much the same way that, like I said, that any massed particle that enters the solar system is entering the gravitational field of the sun. Now, we want to get a good idea. There's some difficult concepts here, and so I'm going to keep coming back to this metaphor of a topographical map. So we have a lovely image here of Sylvan Lake. I don't know where Sylvan Lake is here, um, but if you've ever gone hiking or something, you've looked at a topographical map like this. And what this is saying is, okay, Sylvan Lake is at one elevation. And then these lines tell us that as we move um, through the landscape, we're actually moving uphill. So this has an elevation of 8,800 feet here, and that would be 9,000 and 9,200 and so forth. So we've got a steep hill over here that comes down, and then there's sort of a nice valley here with an open area and a beautiful little mountain lake. So what happens if I were just smooth this out? What happens if I drop a ball here? Well, we know it would roll down the hill, right? But if I dropped a ball here, it would just sit on this nice flat plane. Um, this illustrates a gravitational force field. Okay, it shows the potential movement of an object that's placed in these fields. And that motion is going to be perpendicular to these what are called topographical lines, right? These are going to go in this direction down the hill. Here, this one's going to go a little bit more off in that direction. The ones on this other side of the valley are going to roll down the hill in this direction. And so there's a relationship between the topographical lines and the direction in which that a force would be applied to an object. Okay. Now, the other thing that we can note here is here the lines are very close together. That tells us that it's very steep, right? Because you don't have to go very far before you go up significant elevation. In other words, the slope of this hill, in that sort of literal sense that we use it to talk about landscape, the slope of this hill is very steep. The slope of the hill down here is very shallow, right? You're not really changing elevation levels unless you walk a long way. Why are we talking about topographical maps? Because this is exactly what an electrical field diagram is going to show us. So let's make that connection. So we can make a diagram like this to show the topography of the electrical field around a charge. We have our topographical lines here, right? But over here we have those same lines. These are called equipotential lines. And what this diagram tells us is where a positive charge would go if I put it in this field. Okay, if I put a positive charge here, I know it's going to be repelled by this large positive charge there, and so it's going to move in that direction. That's what that arrow tells me. Positive charge here is going to go in that direction. A positive charge there is going to go in that direction. A negative charge is going to go backwards along these lines. So I put a negative charge here. It's going to be attracted to that large Q in the center. Why is this like a topographical map? Well, a couple of ways. One, if the lines are close together, that means the force on the object is going to be larger. Just as the force on this object here is larger when it's near this top of this hill. We can also see that the lines of action are perpendicular to those topographical lines in the same way that the lines of action here are perpendicular to our equipotential lines. Now, this describes really Coulomb's law. Okay, Q is our big Q. Little q is wherever we're going to put a charge. And this is going to tell us where the force is and how strong it is. So as R gets larger, our force gets smaller. And that we can see by the distance between the lines here. As we get farther away, that distance gets bigger. As we get close, those lines get closer together. So if we think of this as a kind of hill, what shape of a hill is it? It looks like this, right? As long as I'm dealing with a positive charge, if I put a positive charge right here, it's going to roll down very quickly. There's going to be a large force on it, and it's going to roll down that hill. If I put it out here, it's still going to roll away from the center, but it's not going to have nearly as much acceleration to it, not as much force. So this is a topographical image of an electric field. So let's look more carefully at this example. As we said, the blue arrows here are the lines of action. Okay, those are our field lines. The green lines are equipotential lines. And the arrows tell us what direction a positive charge would move if it was placed in this field. So we can imagine it as this sort of hill, right? This is our what our hill looks like for this image. If we place a ball close to the center of the field, like this blue ball is here, or this blue charge is here, we would expect a lot of acceleration, right? That's going to accelerate very quickly down that steep hill. In the same way, this blue charge is going to accelerate very quickly away from the positive charge Q. The red charge is also here. We're still going to roll away from the center, right? It's just going to accelerate more slowly. And we can see that in this image because it's farther away. And because those lines here, those equipotential lines are farther away, that gives us a clue that the force on this red charge is going to be smaller than the force on that blue charge. If both Q and Q are positively charged, what direction will little q move? Well, we know it's going to move in the line of those field lines, the lines of action. If it's a negative charge, it's going to move towards the positive charge, right? So against those field lines. If we wanted to calculate the force on Q at these various points, we could go back to Coulomb's law, right? And so Coulomb's law tells us the force has to do with the size of the two charges divided by the radius squared. So that's why the force here is so much larger, because our radius is small. And so when that's small, this number is small, which makes F big. When my radius is larger, if R is large, then this term is quite large because it's squared, and that's going to make my force smaller. Okay, so this is the hill that's created by Coulomb's law, by a single point charge. Now, beyond being able to explain what's happening in these images, we also want to be able to talk about what the electric field is in that space and define the electric field. We don't just want to know what the force on, say, this charge Q is. We want to know what's going to be the force on any charge that we place anywhere in this field. And so to do that, we're going to take the force, we could calculate the force at any point on this plot, and we're going to divide by our little q. Okay, so what that's going to do is we're going to have Coulomb's law here, but we're going to remove the little q from it. So all that we're going to have left is an expression of what effect that big charge q has on this electric field. So here we take force divided by that Q. We're going to call that our electric field, okay? And that's going to actually get rid of that little q, and so we have a definition here of the electric field. It looks a lot like Coulomb's law, it just doesn't have the little q in it. What this bold here suggests is that this equation covers the whole field. At any given point in this field, I could figure out what R is, and I could tell you what my electric field there is. Okay, and notice the units are newtons per coulomb, so I would know what the force is as long as I knew how many coulombs the charge that I was putting into the field. So if I took a 1 coulomb charge and placed it right here, I would know what the force on that charge was, either a force in the downward direction if it were positive charge, or a force in the upward direction if it were a negative charge. So that's electric fields.